This is the second video presentation from Lesson 2. We're going to be talking about Chapter 10, which is Properties of Materials. Okay, so mechanical properties of materials. So that's mostly what we're concerned with in engineering, mechanical engineering. So what we want to know is what are the mechanical properties of material? And that determines how the material will behave when loads are applied to it. For example, modulus of elasticity, the modulus of rigidity, and strength. These are all mechanical properties. A common method for determining a material's mechanical properties is the tension test or tensile test. So the tension test is a standardized test where an increasing tensile load is applied to a prepared specimen while load and deformation are measured. That's either in increments or in real time. And this is the specially prepared specimen. It's approximately a ½ inch in diameter, and then it's got threads on both ends to mount it in the machine, and then it's got a 2-inch gauge length, and then the load is applied. So here is a picture of a tensile test. You can see the jaws here that grab the part, and then this thing right here is called an extensometer, which measures the deformation of the part as the load is applied. So during the test, load and deformation are measured. Therefore, stress is used to calculate stress is calculated from the load, and then strain is calculated from the deformation. And then from this data, we can get a stress-strain diagram. So much important information about the mechanical properties of the material is derived from the stress-strain diagram. Okay, so here's a typical stress-strain diagram for a ductile steel, usually low carbon. Okay, points I want you to find out here and derive from this are the proportional limit. Okay, that's point A. Okay, so the deformation of the part here is proportional. The slope of this line right here, that is your modulus of elasticity. Point B is the elastic limit. That's when you start getting deformation is permanent. I'm not going to distinguish between upward and lower yield points. The ultimate strength or tensile strength is point E, and that typically is the maximum stress that a point can carry. Okay, that's the ultimate strength. And then less useful is rupture strength, F. Okay. Some definitions for you. Stiffness, material stiffness. That's the resistance to deformation under a load, determined by the material's modulus of elasticity. For example, if you had a stiffer material, it would have a larger modulus of elasticity. It wouldn't stretch as much if it has, under the same load, if it has a higher E. Now rubber, for instance, has a very low modulus of elasticity, so you're going to get deformation in it at lower loads. So think of modulus of elasticity as material stiffness. Now strength. We're always very interested in strength as designers and engineers, mechanical engineers. So yield strength. Beyond the yield strength, large strains result without carrying any more loads. Okay, so that's any spot in the stress-strain curve where you start getting large strains and you're not carrying any more stress, then the part is yielding. Okay, and then the ultimate strength, we talked about that on the last slide. That's the highest point on the stress-strain diagram. It's also known as tensile strength. So I want you to think of tensile strength and ultimate strength is the same thing. Here's another definition of necking. Necking, that's a localized decrease in diameter as the specimen stretches. This is characteristic of ductile materials, this necking down. I want to talk a little bit about plastic deformation and elastic deformation. Okay, so plasticity. So ductility, that's the ability of the material to be stretched considerably before rupture. Okay, let's go back a few slides. So this one right here, okay, you got a lot of deformation going on here before the part fails. This is a very ductile material. That's what that means. Whereas if you had a brittle material, ductility and brittleness are the opposites of each other. What'll happen there with the stress strain diagram, it'll just come up to a point and it'll just fail. It's not going to stretch, it's just going to break. So ductility and brittleness are opposites. How do you measure ductility? That's a term called percent elongation and the percent reduction in area. I have a slide here that shows you pictorially what that means. Okay, so what happens is you start, like, C is the original gauge length, and then D is the final gauge length. Okay, well, the part broke, but you can kind of gauge how long that thing is. So the percent elongation would be the increase in the gauge length over the original gauge length. Okay, that's this equation right here times 100. And then the other one to look at is percent reduction area. I know the part failed, but you can kind of measure here B what the diameter is when it failed. So these two properties of a material are a measure of the ductility of a material. Okay, now some materials don't have a very well-defined yield point. And so in which case we base this on 0.2% strain. Okay, so what we'll do is we'll draw a line, and we'll get a stress strain curve here, right? Take the stress strain curve, and then we'll draw a line starting at 0.2% strain, and then we'll draw that parallel to the modulus of elasticity here. And then wherever it intersects the stress strain curve, we're going to come over here and pluck that off and call that the yield strength. Okay, so any materials that doesn't have a well-defined yield point, yield strength is going to be determined by this method. You'll see that published in a lot of materials data. Some other definitions for you are resilience and toughness. I want you to think of resilience as operating here in what we call the elastic range. Okay, so up into the elastic limit, what's going to happen here is your part's going to stretch, and then the part will come right back. That's called elasticity. Whereas plastic deformation is any deformation that's permanent. Okay, so any deformation that's permanent is called plastic deformation. Any deformation that's, you might have skipped a slide here. Let me go back. Okay, elastic range. Elastic range, deformation is not permanent. Okay, material will come right back at its preload form. Okay, think of it this way. You get a bar, you apply a tensile load to it. That bar is going to stretch. Okay, that's your strain. And then, as long as you don't exceed the elastic limit, when you take that load away, boom, it's going to come right back to where it was. Okay, so that's elastic deformation. It's not permanent. Now, elasticity, that's the ability of material to deform without taking permanent set. What's permanent set? Permanent set is permanent deformation. Now, once we talk about permanent deformation, we're talking about the plastic range. Deformation remains after the load is released. And the term plasticity, that's the ability of a material to deform outside the elastic range without rupture. If we go back to this slide right here, we can see this is the elastic range here up to the elastic limit B, and then beyond that we're talking about the plastic range. So elastic deformation is reversible, plastic deformation is not. Okay, let's go back to resilience. Resilience takes place in the elastic region. That's the area under the stress strain diagram. Now, toughness is the ability of material to handle impact loads. And then the other term I want to throw at you is malleability. That is, a material can handle plastic deformation in compression without rupture. I want you to think about, hammering a bar of steel to change its shape. Okay, if you can do that without the part breaking or fracturing, then that material is known as malleable. This is just a chart of some important metals, just a chart of some numbering systems for steel. Let's talk about allowable stress versus calculated stress. In design problems, we will have an allowable stress. That's the maximum stress level that is considered to be safe when a member is subject to loading. Now, typically in a design problem, you'll be given an allowable stress, and then you'll have to calculate what, let's say, how thick a member is to be able to handle that load within that stress level. And then calculated stress is just the stress that you calculate. Factor of safety. Okay, so factor of safety is typically how you get an allowable stress. Okay, so the failure, the stress at which a part fails, divided by the allowable stress. So what happens here is you're determining a factor of safety. That's how much stress you can handle when you're calculating what your allowable stress is. Chapter 11, all I really want to talk about here is Poisson's ratio. Okay, so when you got a bar in tension, for instance, that bar is going to stretch a little bit. But that stretching in the axial direction is going to be accompanied by a decrease. I'm not talking the necking down thing. I'm just talking about a decrease in its axial dimensions. Okay, so what's going to happen when you we'll show this diagram here. Okay, so I'm applying a load, P. So in the axial direction, our bar is stretching. But in the transverse direction, what we have here is a decrease in diameter. Okay, so Poisson's ratio is actually a property of material, and it's defined as transverse strain divided by axial strain. And it's also related to the modulus of E, rigidity, G. And textbook gives you this equation.